Okay, so I repeat briefly. Now I have to recall what is the covariance mostly for the second year students who participate in the course. So let us consider two real valued random variables. Then this is the variance of the random variable, and by the covariance we call the expectation of the product psi minus its expectation times eta minus its expectation. So that the covariance of the random variable is itself, this is just the variance. Covariance actually measures, somehow it measures the rate of dependency of this random variable. So now I'll explain in more details. But before, let me also know that simple computation, this is just simple computation, shows that the covariance can be found by another formula, expectation of psi times eta minus product of the two expectations. So this is a similar similar with the formula for the variance. Let me also introduce the following object, which is called correlation coefficient. Correlation coefficient. I will denote it by R psi eta, and it equals to the covariance of the random variables psi and eta normalized over the product of the variances, but I should take the square roots. So in such a way, in this way, the degree of polynomial in the numerator equals to the degree of the polynomial in the denominator, because here you have the second degree because of this product. Here you have variance. Each variance is also of the second degree, and then you take the square root. So this product is also of the second degree. And the following proposition makes clear what is the covariance proposition. First, if psi and eta are independent random variables, then their covariance, of course, as well as their correlation coefficient, equals to zero. And the second statement, yes, and the inverse statement is not true. And the second statement is that if psi, that the correlation coefficient is bounded in absolute value by 1, and it equals, its absolute value equals to 1 if and only if psi and eta are linearly dependent random variables. Here a and b are just some numbers. Of course, this property should be held almost surely. So let me prove the first assertion. I just compute the covariance of the two random variables. I write down, okay, I can write down this shortened formula. But since the random variables are independent, the expectation of the product equals to the product of the expectations. And then the covariance is 0. So the proof is trivial. The fact that there exist random variables such that the covariance is 0, but they are not independent, I will leave it as an exercise. as your homework. So this is homework. So I suggest you to find an example for which this holds. But anyway, if the random variables, if their covariance is 0, so we can say that in some sense they're like rather independent. So they behave similarly to independent random variables. So these examples where the covariance is 0 but the random variables are not independent, these examples, they are quite special and artificial. So somehow we can say that the covariance or the correlation coefficient measures the rate of dependency of the random variables. And you see that the correlation coefficient achieves its maximal value, just 1, when the random variables, they're very strongly dependent. That is, they're just linearly dependent. Okay. So let me prove now the random variables for which the covariance is 0 are called uncorrelated. Uncorrelated. So uncorrelated random variables is not the same as independent, but it is somehow close. So the second assertion, to prove the second assertion, let me denote by, say, f xi minus its expectation. So I shift the random variable xi, and also I shift the random variable eta. And now covariance of xi eta, this is just expectation. So it was the expectation of the product of this by this. So now it's just the expectation of f times j. And moreover, we know that expectation of f equals to the expectation of j and equals 0, right? So these are centered random variables. One says that the random variable is centered if its expectation is 0. Centered random variables. Well, and now let us note that this thing, this expectation, f times j, this is a scalar product. I mean, it's easy to check that all properties of the scalar product are satisfied by this expectation. But this is scalar product where? It's scalar product in the space of centered. So the expectation should be 0. Expectation is 0. Random variables, real valued random variables are satisfying. Let me call this random variables xi. Okay, xi is already occupied, so it will be zeta, satisfying that the property that the second moment is finite. So the expectation of the squared random variable should be finite. So it's easy to check that this is a scalar product. So this is exercise. But then, since this is a scalar product, the Cauchy-Bunyakovsky, or Cauchy-Schwarz, as you wish, inequality, Cauchy-Bunyakovsky inequality implies that the expectation of f times j is bounded by what? By the norms, the product of the norms of these random variables. So by such a square root, right? but it means that of course that this color product normalized over this square root is bounded by 1 in absolute value. Yes, sure. Here I should also draw the absolute value. But what is this? Look, this object in the numerator, this is just the covariance. And these objects, look, this is just the variance, because the variances of psi and eta, because by the definition of f and j, this is just r psi eta. And then it remains to establish that this coefficient takes correlation coefficient takes maximal value when the random variables are linearly dependent. But this also follows from the Cauchy-Banyakovsky inequality, because it says that here we have an equality, we have the equality if and only if what f is linearly dependent with j, but now it isn't a affine space, it's a linear space, so f equals to a constant times j. But this means that psi, so what is f? This is psi minus expectation of psi equals to c times eta minus the expectation of eta, and this gives that psi equals to c times eta and plus some constant which is given by the expectation of psi minus constant c times the expectation of eta. And here I should write not f but eta. Okay, so indeed we see that psi is linearly dependent with eta, because this is the constant a, and this is the constant b from the formulation of my proposition. Okay. So indeed, in fact, I will not use this proposition. I will use only the covariance, but I will strongly use the fact that covariance is small. In some sense, means that random variables behave as if they were independent. And this proposition just shows you how the correlation is related to the property of independence. Okay, any questions or comments? Well, if no, then I go back to Markov chains, but in fact not immediately to Markov chains. I will start with recalling you the standard result from another standard result from the probability theory, which is the law of large numbers. Law of large numbers. Because my main goal for today is to prove, or at least to start proving, law of large numbers for Markov chains. So it turns out that, so you know, and many of you know that the law of large numbers is satisfied once your random variables are independent. It turns out that it also satisfied for the case when the random variables form exponentially ergodic Markov chain. And my plan is as follows. First, I will recall you just the standard law of large numbers. So I will start with the classical setting. I will even prove it, and then I will pass to the Markov chains, because the scheme of the proof for the Markov chains is, I mean, the same that for the independent random variable in the classical setting, but since the random variables in the Markov chain, they are not independent, it becomes much more technical. And I think that this is the most technical proof in my course. Okay, so those of you who is familiar with the standard law of large numbers can, I mean, you know all this, what I'll be talking about. Let me introduce a couple of definitions. So let's assume that we have random variables psi0, psi1, psi2, etc. And let me say that these are real valued random variables. Real valued random variables. And definition. Assume these are real valued random variables on the probability space omega from sigma algebra, and the probability p, and psi is also will be a random variable on this probability space. And we say that the sequence sorry, psi n converges to the random variable psi in probability, and we denote it like that with the letter p above the arrow, converges in probability if for any positive epsilon, probability of the event that the difference between psi n and psi is more than or equal to epsilon, converges to 0 when n goes to infinity. So you see, I look at the event where psi n is not very close to psi, right? And for any epsilon, the probability of this event should go to 0. This is a rather reasonable definition of convergence. In fact, for what is a random variable? Random variables is just a function from our space of elementary events to real numbers. So as for any functional space, we can imagine plenty of different topologies, so we can imagine plenty of different convergences. This is one of the most used in the probability theory and one of the most reasonable. As another example, let me mention that there is another type of convergence which is called almost sure convergence. This is just the following thing. Okay, so let me write it also as a definition. Psi n converges when n goes to infinity to psi almost surely if I would like to write down the following thing. I would like to write down just that for every omega, I have the convergence. So this is just the point-wise convergence, the simplest type of convergence. For at any point, the values of our functions converge. But in probability theory, this doesn't work well, because in probability theory, just any omega, it isn't interesting. It's interesting that the probability of the omegas such that this holds, this convergence holds, equals to 1. Because in probability theory, if something happens with probability 0, so other omegas for which we do not have the convergence, the set of these omegas has probability 0. Events of probability 0 aren't interesting for us. So I can say that this convergence holds not for every omega, but just for the set of probability 1, right? And I call such convergence almost surely convergence. This is the simplest one. This is the simplest convergence. And for example, if I know that so this is a proposition which I will not prove. This is a standard proposition. Most of you know this well. If I have almost sure convergence, then I have convergence in probability. But I have the convergence in probability. But in the other direction, it doesn't work. In fact, in some sense, it also works in the other direction. In the other direction, we can say that you can choose a subsequence of the sequence which converges almost surely. So once your sequence converges in probability, you can choose its subsequence such that it converges almost surely. But well, let me skip it. So I explained what is the almost sure convergence just to give you some idea that the convergence is probability. In probability is not unique possible convergence in the probability theory, but there are many of them. But this is one which is rather reasonable and rather convenient. There are also some weaker convergence, for example, the convergence in distribution, which is also very reasonable. And I think it's even more used than the convergence in probability, but today I will use the convergence in probability. Well, exercise. This will be your homework. This is also standard facts from probability theory. So let us assume that we have sequence of random variables xi n, random variable xi, and another sequence of random variables eta and random variable eta, and they all live on the same probability space. They are all real valued. And moreover, let us assume that xi n converges in probability to psi, eta n when n goes to infinity, eta n converges in probability to eta when n goes to infinity, and then I claim that it's a very natural thing that the sum of eta psi plus eta n plus xi n converges in probability to the sum of the limits. So this is our convergence wouldn't be very convenient if this property did not hold, but it holds. But it holds, and this is an exercise. Actually, it is not just so immediate because you see the definition of the convergence is not so simple, but nevertheless this is a quite simple exercise. Well, in particular, if an is just a sequence of real numbers, числовая последовательность, then and we know that an converges to some limit a, when n goes to infinity, just in the usual sense, in the sense of sequences of real numbers, then if we take our sequence of random variables psi n and add to it a real sequence an, then it converges to the sum of psi plus a. But actually just to understand, are you still alive or not, I have the following question to the audience. What does it mean, psi plus a? Because psi, this is a random variable, and a, it is a real number. What does it mean, this sum?
A is also a random variable, but it takes a certain value with probability equal to 1.
Yeah, so we can just think that a is a random variable, which is identically, so, well, I can associate with a the random variable, let me call it a tilde, which is identically equal to a for any omega. For any omega, here I can just write down any omega, not just the set of omegas of probability 1, but just any omega. Okay. Well, now I reminded you what is the convergence in probability, and I'm ready to formulate the classical law of large numbers, LLN, law of large numbers. Turing. But actually, do you remember what was the number of the last statement from the previous lecture? Because I'm trying to enumerate all statements, and I forgot the number of the last statement. It was not online. It was on the Blackboard, so I cannot check.
I have the last corollary with the number 24.
24, perfect. Thank you. I think that this is correct. So I'll leave all the story about the correlation without numbering. Okay, let me call this proposition by number 25. Okay. No, I do not need this proposition, so I will leave it without a number. But this exercise, this will have number 25. Perfect. And the theorem, then it's theorem number 26. So this is the simplest form of the law of large numbers. Let psi 0, psi 1, psi 2, etc. be a sequence of independent random variables independent real valued random variables on the same probability space, satisfying the relation that their variance is bounded uniformly uniformly in J. Uniformly, I mean that there exists constant C such that for any J we have what is written here. Okay, so all the variances are bounded by the same constant. Then, so in particular, the variances are finite. Then let me consider the random variable Sn, which is just the sum of the first n random variables xi j, xi k from my sequence. So I take the sum from k equal to 0 to n minus 1 xi k. And the theorem affirms that this random variable satisfies the relation, the following relation. I subtract from this random variable its expectation. So now I consider the centered random variable, and then I divide it over the number of terms in the sum Sn. And it turns out that this goes in probability to 0, and then goes to infinity. So what does it mean? To make it the meaning of this assertion more clear, let me consider example. Example when so I'll write it as follows. I'll write in particular if, so in my example, I assume that all psi j are identically distributed. Identically distributed then their expectations, in particular, all their expectations are the same and just equal to the expectation of the first random variable. And then the expectation of Sn over n, this is just what is this? This is n times expectation by linearity of the expectation of the first one, and this is then just the expectation of the first one, psi 0, and this means that our theorem affirms that Sn over n minus this expectation goes to 0, but by this property, that the convergence in probability supports so we can add one sequence to another sequence, support summation, then it means that this guy converges to the expectation of psi 0 in probability and then goes to infinity. So most of you are familiar with this statement, but nevertheless, for those of you who are not, let me comment on this. Is a very, very nice thing, because look, okay, so let me consider an example. This is really simple. Example, so another one example, just more concrete. Let's assume that I have a coin, and I throw it, and I look if I have head or tail. Значит, я монетку бросаю, смотрю, орел или решка. And psi I equals to 1 if I have head, say, значит, если орел, то тогда у меня xi равно единичке. And the probability, let me say that the probability of the head is 1 1/4. Okay, and the probability of the tail, значит, вероятность решки, probability of the tail, and I write down 0 if I have tail. This is accordingly 3/4. Then what is Sn? So what is Sn? Who can say? What is the meaning of Sn? Is what? What is this? Что такое Sn? Какой смысл в этом?
Empiric mean of tails or what?
Sn is just a number of heads.
Yes.
Once.
Yes. It is not mean because because we do not divide by n.
Is number of heads. So this is if I have head. So число орлов, number of heads, and Sn over n. This is the rate. Значит, доля of heads. Доля орлов. Okay. So our statement says that, yeah, and the expectation of psi 0, this is just what? It is just 1/4, right? So we get that the rate of heads just converges to 1/4. So мы получаем, что частота орлов, с которой вы бросаете монетку, вот сходится в таком случае к одной четверти. So if I had here one second and here 1 second, so the coin is just usual coin, then I would have that the rate of heads asymptotically is the same that the rate of tails, which is not surprisingly, right? But this is a mathematical theorem. This is a mathematical theorem, and what is nice in this theorem is that actually here in the left hand side you have a random object. This random object, but it converges to a deterministic object, right? It converts just to a number. So this is the law of large numbers. So usually in applications it's used just to understand what is the rate of some events. For example, as in this example. Okay. So, do you have any questions on the law of large numbers? No questions. So let me just prove it. Proof. Wow. Before proving it, I have to recall another thing, which is the Markov inequality. It's a very well known and frequently used inequality from the probability theory, which says the following: let eta, I will not prove it, but you can find proof in a textbook, and or you can just try to prove it by yourself. This is not complicated. This is not complicated. This is a proof in one line, but I mean, you should, if you have never seen it, so it can take time to find this proof. Well, let eta is non-negative random variable, so it means that eta of omega more than or equal to 0 for any omega. Of course, I should not write here for any omega. I should write here for the set of omegas with probability 1. But let me keep it as it is. Then probability of the event that eta is more than or equal to epsilon is bounded by the expectation of eta divided by epsilon. Look, of course, when this inequality is useful. Of course, if the right-hand side is more than 1, so if epsilon is small, then I mean it isn't useful because you anyway you know that the probability is bounded by 1. But if if epsilon is large, then it is useful because it says it estimates the probability of your random variable to be very large. So here you should think about epsilon as about a large number, not small number, but large number, which is unusual for the letter epsilon. But I don't know why, but in standard formulation, people write here epsilon. But this you should think about epsilon, I repeat again, as about a large number. And corollary of the Markov inequality is the Chebyshev inequality. Chebyshev, точнее говоря. Chebyshev inequality. Chebyshev inequality, it affirms the following. So let the expectation of random variable psi of its absolute value squared, let be finite. So in fact, this means that its variance is finite. Then, of course, here I should assume that the expectation of eta is finite. I should assume it, right? In the Chebyshev inequality, I have the following relation: the probability that psi deviates from its mean more than epsilon, it is bounded by the variance of psi divided over epsilon squared. Again, you should think about epsilon as about a large number, not as about a small number. Proof of the corollary immediately follows from the Markov inequality. Look, this guy equals to the probability that square. So you have two positive objects. On the left-hand side, you have the absolute value. On the right-hand side, you have positive number, and then you can take them. You can take squares of the both sides of this inequality, and then you can apply Markov inequality to this random variable, which I call eta, and by the Markov inequality, it is bounded by the expectation of eta over epsilon squared. But the expectation of eta, what is this? Just by definition, this is the variance of psi. You see, so Chebyshev inequality and Markov inequality are almost the same. And, personally, I often like I forget what is called Markov and what is called Chebyshev. It isn't very good, of course, but this is indeed almost the same. Okay, now let us return to the law of large numbers. What do we wish to prove? We wish to prove that such an object converges in probability. Very good. In probability to 0. Very good. Let me try to prove it. Proof of the law of large numbers. So I should study the probability of the following form: that this guy is more than or equal to epsilon, right? And I should prove that it converges to 0. I should prove it, right? This probability equals to what? Let me multiply the both sides of the inequality by n, and then I will get the deviation of my Sn from its mean in the left-hand side, but in the right-hand side, I will get epsilon n. And by the Chebyshev inequality, inequality, in Russian, I have already learned that Chebyshev is not Chebyshev, but Chebyshev, but in English, I don't know why I often pronounce Chebyshev. It is bounded by the variance of Sn over epsilon n squared, epsilon squared times n squared, right? Right. This is indeed just the Chebyshev inequality. Perfect. But what is the variance of Sn? What is the variance of
It's sum of variances of psi.
Yeah. So what is Sn? Sn, this is just sum from k equals 0 to n minus 1 psi k. But they're independent. They're independent. And we know that the variance of psi plus eta equals to the variance of psi plus the variance of eta if psi and eta are independent. Right? Then by the independency of my psi k, by the independency of my psi k, here I get n times the variance of psi 0 divided over epsilon squared n squared. And you see, in the result, I have just variance of psi up. Sorry, why? I didn't assume that psi are identically distributed. I assumed it only in my example, but I assumed that psi are identically distributed only in this particular case. But in the main statement, I didn't assume that. But I assumed that all the variances are bounded uniformly by the same constant. Well, so let me then write here what I have. I have sum of all variance psi k, and then I will use that these variances are bounded by the same constant. I will get here n times this constant c over epsilon squared n squared. This is just c over epsilon squared n, and this goes to 0 and then goes to infinity. That's it. You see, we have proven the law of large numbers. The proof is indeed very, very short, just one line. Just you write down what you wish to establish. You wish to establish the convergence in probability, you write it down, and then you just use the Chebyshev inequality first and the independency of your random variables second. Well, let us remember it and let us pass to the Markov chains. But before, let me mention that in fact, law of large numbers holds not only in this statement, in this one, not only in this one, but also in a stronger statement where the convergence in probability is replaced by the almost sure convergence that we have already discussed today. The proof is more involved. I will not show it to you, but again, you can find the proof in any textbook. Well, So now let us go to Markov chains. Just a second. Okay, yeah. So law of large numbers for Markov chains. For Markov chains. What time is it? We have like 25 minutes. That's perfect. Let's assume that we have a sequence. Now, this sequence is not a sequence of independent random variables. This is a Markov chain. Markov chain with a state space пространство множество состояний, state space X. State space X. So usually we just enumerate these states by 1, 2, 3, 4, etc. So as usual, you can think that this X is just 1, 2, 3, 4, etc. And then the number of states in most of our examples is finite, but in principle you can think about an infinite number of states as well. Look, I would like to do the same thing as for my my independent random variables, which we studied before. So I would like to consider the following object Sn, which is equals sum from k equals 1 to n minus 1 of psi k. But this is, I mean, this doesn't make many sense because it doesn't make a lot of sense because look, I mean, state space X. So these random variables, their values belong to the state space X. This state space X is some abstract object. If you think that it is 1, 2, 3, 4, then it means that these random variables take only values 1, 2, 3, 4. This is not so, I mean, so natural and so interesting. It would be much more natural if instead of this object, I considered the following object. Let me take any function f, which maps this state space to real values. And then I will consider instead of the random variables psi k, I will consider the random variables f of psi k. And I will define Sn accordingly. This is a sum from k equal to 0 to n minus 1 of the function f of psi k. It doesn't make sense to introduce this function in the standard setting of the law of large numbers, just because you denote this f of psi k by eta k, and you apply again the same law of large numbers. So it doesn't make any sense to write here the function of psi k. But here it makes sense, in particular because of the following property. This is something between remark and exercise. I don't remember if I have already given you this exercise for homework or not. If not, I will give it. Exercise. Look, if psi 0, psi 1, psi 2, etc. is a Markov chain, then if it is true that f of psi 0, f of psi 1, f of psi 2 also is a Markov chain. How do you think if it is true or not?
I think we had to require that F was injective, right?
Yeah, if F was bijective, then this is true. But if not, so in general, this is not true. In general, this is not true. You see? So when I introduce this function f here and consider this object instead of this object, indeed I consider some like much more. This statement is much more involved. The statement is much more general because this sequence, it is not anymore a Markov chain for many functions. You see, this was an explanation why I introduced this function f. Okay, this was some motivation for this. Well, let us go further. Let me give some example. If the function f okay, let us say that some x small belongs to x large, x hat. Well, if f of x hat equals 1, let me write down. Let me put it as follows. If f of x equals 1 for x coinciding with certain x hat, and 0 if x is different from x hat. So I fixed this x hat. Then what is Sn, which I recall is the sum of f of psi k from k equal 0 to n minus 1. What is this? What is the meaning of this object? This is a number. So you want to say something?
Yes, it is the number of x hat in the Markov chain from
So yes, this is the
0 to
number
n minus.
of times that I visited that okay, not I, but the Markov chain visited the state x hat, right? So here I have the state x hat, and I just compute the number of times I arrived there. And then Sn over n, this is the frequency of visiting the state x hat. So you see, indeed, this introduction of this function helps a lot to consider some natural objects. Well, before formulating the theorem, I will have to introduce some more notation. Let the function f. So let's consider the function f as before, and let us consider any distribution P. So I recall the distribution. It means first that sum of its components equals to 1, and second that all components are non-negative. So this is the vector Pj, j is from x. The sum of Pj equals to 1, and faulty j are non-negative. This is a set of all distributions. I've used this notation before. Then I will denote by the following via the following notation, brackets, sorry, brackets of such form, such triangular form, the distribution p, the function f, the action of the distribution phi to the function f, in the sense that this is just the sum over j from x p j f of j. Okay, so in particular, if p, this is a distribution of a certain random variable eta, distribution of a random variable eta, which takes values in the space x, then what is the action of its distribution to the function f? Huh? What is this? P eta j, f of j. What is this? What is
expectation of f with respect to
Yeah.
p eta?
Exactly. Because look, what is p eta j? By definition, this is the probability that eta equals to j. What is the components of the vector of distribution of random variables? This is probability that the random variable takes the corresponding value, right? So I sum the probabilities times the values of the function computed at this state j, and this is just by definition the expectation of f of eta. You see? So this is very natural object. Well, the last reminder before the formulation of the theorem. This is the reminder about the last lecture. A Markov chain is called exponentially ergodic if what? If it has a unique stationary state pi, and they exist, and the convergence to the stationary state of distributions of this Markov chain is exponential. More precisely, there exists constants c, which is positive, lambda, which is in between 0 and 1, such that for any initial distribution pi 0, the corresponding distribution at time n, its distance from the distribution for the steady distribution pi in the L1 norm is bounded by constant to the constant times lambda to the power n. Okay, and the L1 norm, this is just the sum of of absolute values of all components of the vector. So now let me formulate the main. Any questions? No questions. So now let me formulate the main result for today. This is the law of large numbers for the Markov chains. This was the theorem number 27, I think. So, right? This is, yes, this was 26. So now it should be 27. So theorem 27. This is law of large numbers for Markov chains. Wow. No, wait. Unfortunately not. Unfortunately, before formulating the theorem, I have to prove another small lemma. So this will be lemma 27. Lemma 27. If a Markov chain, our Markov chain, xi0, xi1, xi2, etc., is exponentially ergodic, then the expectation of the function f computed at the at xi(n) minus the action of the stationary distribution pi to the function f is bounded by some constant. Let me call it c tilde lambda to the power n. Look, lambda, this is the same lambda that in the definition of exponential ergodicity, but c tilde, this is some another positive constant. So the proof is, as usual in our course, is simple. Look, what is this expectation? What is this expectation? This is the summation from J over the summation over J from X probability that xi(n) equals to J times the what times the value of the function f at the state J, right? So this is the summation of the component number J of the distribution pi n times the probability f of J. But this guy, look, this guy, okay, yeah, I want to say that this guy converts to its component have to converge to the components of the stationary state. More precisely, I have the following. Now, if I write down the difference I am interested in, then I get the sum over all components of over all states J of what? From this guy I have Pjn from this action. This action by definition, I recall that this is a similar summation, but here instead of Pjn you should put the components of the vector pi. So that's why here I subtract pi, and then I write down f of J and this is bounded by subnorm of the function f times the L1 norm of the difference between pi and Pn. And here I should assume additionally that the function f is bounded for any bounded function f. I will also denote today and in the next lecture by f infinity its supremum norm. So this is a supremum over all states of the absolute value of the function f. Well, look, then this holds. This trivially holds, right? But this guy is bounded by the exponential ergodicity by constant times lambda to the power n. So I've computed my c tilde, which is just constant c times the subnorm of the function f. Okay. Questions? Comments? No questions, no comments. So then finally I will formulate the law of large numbers for the Markov chains. This is theorem 28, law of large numbers for Markov chains. Let psi0, psi1, etc. be exponentially ergodic Markov chain. Okay, now we are always talking about homogeneous Markov chains because the notion of exponential ergodicity and of ergodicity and even of the stationary measure, it doesn't make any sense for non-homogeneous Markov chains. So I did not write it down, but let me write it down. Nevertheless, let me insert it here. Homogeneous Markov chain is called exponentially ergodic if blah blah blah. So now we are considering exponentially ergodic Markov chain with a stationary state phi, and let f be a bounded function. Then the random variable Sn, which is defined as before. So this is the sum from k equals 0 to n minus 1 values of functions on my Markov chain, satisfies the following three convergences. The first one is just the same that for the classical law of large numbers. The centered random variable Sn normalized over the number of over n converges in probability to 0 when n goes to infinity. The second statement says the following, that the expectation of Sn over n, it converges to the action of the stationary measure pi to the function f. And the third statement, which is just immediately follows from the first two statements, affirms that Sn over n converges in probability to the action of the stationary measure to the function f. So now let us look at this theorem. Let us look at this theorem. You see, this is indeed close to the standard law of large numbers. This is the same statement, but let us compare it with the standard law of large numbers in its simplest form for identically distributed random variables. For identically distributed random variables, I recall you that we had simpler. We had the following simplification. We knew that the expectation of Sn over n, this is just the same as the expectation of the first random variable. So it implied that this formula can be rewritten in the following form, that Sn over n converges in probability to this expectation of the first random variable, right? For the Markov chain, we have somehow similar situation. But here Sn over n converges not just equal to constant as in the case of identically distributed random variable, but it converges to some constant, which is the action of the stationary measure pi to the function f. Yeah, here is it, and this implies that Sn over n converges to this number. Actually, this is a question for you. Is it possible to represent this object as an expectation of some random variable or not? What do you think? Возможно ли представить вот эту вот штуковину как мат ожидания какой-то случайной величины? Я хочу показать, что то, что происходит, это похоже на стандартный закон больших чисел в каком-то смысле. So the answer is yes. The answer is yes. Because if I take a random variable eta with distribution with a stationary distribution pi, okay, then the action of pi to the function f equals just to the expectation of eta, because of my just because of this, because of this formula. You see? Maybe it doesn't equal to the expectation of eta. Of course, it equals to the expectation of f of eta. Of f of eta. So we also get that this guy converges to the expectation of something, but of some random variable. But this random variable eta, it does not have. I mean, it has quite complicated relation to the random variables psi k. So our Markov chain is exponentially ergodic, and this means that we have convergence to the stationary state. And it turns out that in the sense of the law of large numbers, so this, I mean, in the sense of this object behaves in the same way as if we considered the sequence of identically distributed random variables eta 0, eta 1, eta 2, etc., which have the same distribution as eta. Смотрите, если бы я рассматривал последовательность случайных величин, таких, каждая из которых имеет вот распределение π, то, значит, стационарное распределение для моей марковской цепи, то вот для них, вот давайте я назову, значит, ну вот Sn это, да, это значит Sn, которое определено с точностью вот таким вот образом. F от это, значит, катая, да, от p равного нулю до n-1. Если бы я вот такую штуку рассматривал бы, то тогда бы вот это Sn это делить на n, оно бы сходилось, значит, тоже к мотожиданию и к мотожиданию, значит, f от это. Вот, то есть получается, so we see that our Markov chain asymptotically behaves in this sense as such a sequence. So this is quite natural because we know that exponentially ergodic Markov chain converges to the stationary state. Well, this was some interpretation to give you some intuition, and now let me give an example, and then I will finish for today. And on the next lecture, I will give you a proof of this theorem. So, example: if I consider the same functions that I have already considered, I fix some state x hat, and I consider the function which equals to 1 if x coincides with f x hat and 0 otherwise, then we have already discussed that Sn over n, this is a frequency of visiting the state x hat, and then pi applied to f. What is this? This is summation components of pi over j from x, f of j. This equals to pi x hat, right? To pi x hat. And this is what is this? This is a stationary probability of the state x hat. And the law of large numbers affirms that the frequency of visiting the state x hat converges when n goes to infinity to its stationary probability. Those of you who are familiar with the ergodicity in the sense of dynamical systems will find that this is exactly that. Look, in dynamical systems, one says that dynamical system is ergodic if its time average converges of observables converges to the space average. In our setting, time average, what is the time average? This is exactly frequency of visiting the state x hat. And space average, this is the like average probability. The space average, this is also average according to some measure, and here the measure is a stationary measure. The space average, this is exactly the stationary probability of our state. So this is natural. If stationary probability of the state is large, then I visit this state quite frequently. Of course, when the process is already going during some long time, because I need to be close to the stationary probability according to the ergodic theorem. And if the stationary probability is small, then I visit this state rarely. Let me repeat it in Russian. Значит, смотрите, если стационарная вероятность состояния большая, то тогда что? Тогда, значит, согласно экспоненциальной эргодичности, я схожусь к стационарной мере, так, значит, я начинаю жить все ближе и ближе к стационарной мере, вне зависимости от начальных условий. И тогда частота моих посещений состояния с высокой стационарной вероятностью, значит, большая. Но вот если стационарная вероятность маленькая, то я там в этих состояниях буду бывать редко. Вот такое вот простое утверждение, которое следует из закона больших чисел. Okay. Any questions? Any questions or comments? So if no, then let us finish for today. The last thing that I will announce, this will be a problem for your homework. The question is as follows: if our second theorem, the law of large numbers for Markov chains, implies our first theorem, the classical law of large numbers, or not? How do you think? Влечет ли закон больших чисел для Марковых цепей классический закон больших чисел? Okay.
We can remove dependence somehow between xi's in Markov chain.
But it should work in the other way. The question actually
no. I mean, we can construct such Markov chain so that xi's are independent.
So yeah, correct. In other way, so putting it in the other way, the question is, if a sequence of independent random variables forms a Markov chain. Okay.
Okay.
So this is the question. Here, since we wish to work with homogeneous Markov chains, of course, we need to assume that these random variables are identically distributed. Well, so let us finish for today, and I will put the homework on the website. I hope this evening. If not, maybe then tomorrow evening. Bye.
До свидания.
До свидания.
Счастливо.